Let me quickly give you an introduction into the chapter 5. Chapter 5 of Oppenheim and Schafer is split into multiple subsections. I'll just give you, since we're doing an overview. So this is chapter 5. It is called Transform Analysis. Transform Analysis of LTI Systems. Okay. We are focusing on LTI systems. Remember, those which are characterized by an impulse response. And we're going to be looking at transform analysis, looking at both Z transform and the discrete time Fourier transform. So, given that we are going to be applying discrete time Fourier transform, you're going to apply some of the properties of LTI systems, you will find that there is a repetition of concepts. But there are also many new concepts that are coming in, and I hope you will capture the new concepts and add it to the concepts that are already studied. So here is a quick summary overview of the chapter. Chapter 5.1 deals with the frequency response of LTI systems. LTI systems. Okay. This we will assume is something that we already know how to do, because if an LTI system is characterized by means of h of n, we can always compute he of j omega. That is the frequency response. Okay, and the frequency response can be written in terms of magnitude and phase, real part, imaginary part, all of these things that we have studied in chapter 2. Now, section 5.2 says that you can use this technique to analyze LTI systems. So, systems characterized by LCCDE. Characterized by LCCDE. Okay, again, this is something that we have already touched upon. We'll just quickly review that. Then comes the rational transfer functions. How do we compute the frequency response of rational transfer functions? If I have a numerator and a denominator expression, I have poles and zeros, how do we calculate that of a rational transfer function? Okay, and here there are two things that we will be studying. The first one is to plug into a tool like Octave or MATLAB and compute the response very precisely. Okay, starting from omega equal to 0 to omega equal to 2 pi, you want to calculate and get the exact expressions for magnitude and phase. The second one, which is extremely important, is not a precise understanding of the magnitude and phase, but an estimate. By looking at it without programming it, without plugging it into MATLAB or Octave, can you guess what the transfer function is going to look like? What is the magnitude response? That is going to give us an intuition to designing of the LTI systems. So that is very important. So the frequency response is going to help us how to design that. And for that we will be studying in section 5.4 the relationship between the magnitude and phase. How does the magnitude vary? How does the phase vary? What is the contribution of poles, what's the contribution of zeros? We're going to be looking at that. So relationship between magnitude and phase. Magnitude and phase. Okay, very important aspect. Then comes a section of a very interesting concept that is there only in discrete time signal processing. It is called an all-pass system. It passes all frequencies. Okay, and then you may ask, what is the use of this? It has got many different uses. We'll just mention that. And of course, we will also be studying two types of LTI systems. LTI systems which satisfy the property that it has a linear phase. Okay, first one is going to be LTI systems which has got a linear phase, a phase that varies linearly with frequency. Okay, linear phase. And in connection with what linear phase means, we will also talk about something called a minimum phase system. Okay, so once we understand these concepts, we have been able to apply the tools that discrete time Fourier transform has given us, and we will have a very powerful set of tools to work with. Okay, so let us get started. I think the important thing is to quickly go over things that we have already seen and spend more time on the concepts that are new that we are going to be looking at for the first time. Okay, so let me see where we are. Okay, I will have to start here. Okay, so we are looking at Oppenheim and Schafer chapter 5 and starting with section 5.1. Okay, LTI system. LTI system. That means the system satisfies the properties of linearity and time invariance and therefore is characterized by an impulse response h of n, as we saw in the second chapter, x of n passing through an LTI system characterized by an impulse response h of n producing an output y of n, input-output relationship. Y of n is equal to h of n convolved with x of n, convolution we have defined. And so we say that an LTI system, if we want to do transform analysis, we can take this h of n and study it using discrete time Fourier transform. Okay. If the discrete time Fourier transform does not exist or you want to have a broader insight, you may go for the Z transform, but mostly discrete time Fourier transform because that is where we are going to be. So using the discrete time Fourier transform, the fundamental relationship is y e of j omega equal to h e of j omega, the convolution property is being used, x e of j omega. Now in the chapter 2, we looked at x e of j omega by itself, we looked at h e of j omega by itself. But now what we are going to say is, hey, I'm not interested in them individually. I'm looking at it as an LTI system for which the input is x of n, output is y of n. I want to look at the relationships that are present in between them. Okay, I hope you are comfortable with the way we are going to be approaching these systems. All right. So when we look at the relationships, we are saying that let's look at h e of j omega. That is the system response or that the response of the LTI system. Now what can you tell me? Again, this is a recap of what we have done. Okay, this is a complex valued function of omega. Okay, that's property from chapter 2. Function of omega. Now this can be analyzed in terms of magnitude and phase, or it can be analyzed in terms of the real part and imaginary part. Okay, h e of j omega is a complex quantity, so therefore you deal it in magnitude and phase or real part and imaginary part. We are going to be focusing more on the magnitude and phase in this particular chapter. This is our interest, and of course keep in mind that h e of j omega is a periodic function with period equal to 2 pi. So therefore all of our discussions will be limited to one period, 0 to 2 pi or from minus pi to pi, and that will give us a complete understanding of what we are interested in. So let me just write down this result, that h e of j omega, we will be looking at it as a magnitude response h e of j omega. This is what we call as the magnitude response of the LTI system, and multiplied by e power j argument of h e of j omega. Okay, argument of h e of j omega. Again, this is a repeat from what we have already studied, and this is what we will call as the phase response argument. phase response. Okay, magnitude response, phase response. Both are functions of omega, both are periodic with period equal to 2 pi. Okay, so both of these, so magnitude response and phase response, both of them are periodic in omega, with period equal to 2 pi. Okay, magnitude will have certain different properties, but at the end of the day, both are periodic. Now, why are we interested in magnitude and phase? Because the magnitude of the output is going to be determined by the magnitude of the input signal multiplied with the magnitude of the LTI system. Okay, very important. Now, maybe to see an example will be more interesting. Supposing I have an input system which is given from minus pi to pi, and I pass it through an LTI system who's got a magnitude response, let us say from minus pi to pi, I'm sketching. It has got a flat response in this portion, and then drops down to 0 and then comes up. Okay, so flat response drops down to 0 and then comes up. Okay, so this green line is magnitude of x, red line is magnitude of h. Now, if you combine these two, what we find is you get the magnitude response of y. It will be a product of these two terms. So, what you see is you will see these frequencies, and then you will see a null, and then you will see the remaining frequencies. So, minus pi to pi, this will be the magnitude of y. So, actually this is a very practical example. If you want to remove the DC component in a signal, what do? You take the input signal, pass it through a filter which has got, it's basically a band stop filter with a very narrow stop band. So, therefore, this is actually called a notch filter. It's a type of band stop filter, it stops only the 0 frequency. This is a notch filter. If you apply the input signal to a notch filter, what you will get? You will get the signal, input signal with the DC component which has been removed, and therefore, so now you can see why the magnitude. So previously we were looking at the magnitude by itself. Now we are looking at it in the context of an LTI system to say, okay, how will the output magnitude be affected by the input going into an LTI system with a specified magnitude. Now, in the same manner, you can also recognize that the phase will also get affected. So, just like we saw the magnitude, we can also say that the angle of y e of j omega will be the angle of h e of j omega, the argument from that, plus the angle of e of j omega. Okay, so when you look at an LTI system, we say that we will look at it in terms of the magnitude response, magnitude h e of j omega, and it is its phase response, argument of h e of j omega. And in both these cases, there may be desirable changes that you are introducing, right? So, the effect of the LTI system is characterized by magnitude and phase, and this effect may be desirable. In one case, let us say that you wanted to remove the DC offset, so therefore you pass it through a notch filter. But maybe there is another scenario where you don't want to remove the DC offset, but the notch filter is there in your signal path. So it can also be a signal of something that is not desirable, which you will have to deal with and understand and say, okay, how is it going to affect my output signal? So whether it is a desirable effect or an undesirable effect, the understanding of what the changes are happening in magnitude and phase are important for the study that we are going to be looking at. Okay, so maybe if we were to write it in words, what we are saying is how the magnitude and phase of the input, the magnitude and phase, okay, the magnitude xe of j omega and argument of x of e j omega, phase of the input x of n is modified by the LTI system. LTI system. Okay. And as we said, it may be a desirable change or an undesirable change, but in any case you want to know what is the impact that it has had. And there is a third one which we also have looked at in chapter 2, which is the impact of the group delay. An LTI system will also introduce a group delay, and as we mentioned, tau of omega is equal to minus d by d omega of the argument of h e of j omega. Okay, it's the imaginary part by real part if you want to write it in terms of the real and imaginary parts. But basically this is so argument of h e of j omega is equal to arc tangent of the imaginary part of the dt of t divided by the real part of the dt of t. Okay, again this is something that we have already looked at, and so the first new result that I want you to learn is something known as the principal value of the phase. Principal value of the phase. Okay, if you ask a program like MATLAB or Octave to compute the phase response, what it will give you is a argument. I'm going to write it in uppercase arg, not lowercase arg, argument of h e of j omega, which will always lie in the range minus pi to pi. Okay, so it's lies in the range minus pi to pi. And why is this always in the range minus pi to pi? Because anything which goes below pi, it maps it back by adding a value equal to 2 pi, it makes it into a positive quantity. Anything above pi, it subtracts 2 pi and then makes it a negative quantity, which is between 0 and minus pi. So basically this is the principal value that you have, and never to get confused or to be misled by the fact that that what we can compute using our tools is always the principal value. Whenever you say arctan, it will come as a value between minus pi to pi. So if I were to say what is the true phase, the true phase of h e of j omega, can we get that? Yes, we can get it. It will be equal to the principal value of h e of j omega, and at each frequency, right? Remember, this wraparound can happen at any frequency. You may have to add or subtract multiples of 2 pi. Okay, so r of omega will be an integer value for each omega. Okay, so integer value for each value of omega. Okay, so let me give you an example, because easy to visualize it in the context of an example. Okay, example. Supposing we were given that our LTI system is a delay with of nd units. Okay, nd is some integer value. So then we know the input-output relationship. Y of n is equal to x of n minus nd. h e of j omega. He of j omega will be equal to e power minus j omega nd. Nd is an integer. Take magnitude. Magnitude He of j omega is equal to 1 for all values of omega. A delay is an all-pass function. All-pass functions are those functions which treat all frequencies the same. Okay, so a delay is trivially an all-pass function. Okay, the all-pass function that we will be studying later on in this chapter are non-trivial all-pass functions. This is a trivial all-pass function, but it has got that. Okay, and it also has a very interesting property, the argument of He of j omega. Argument of He of j omega, if you look at it, it is minus omega nd. And you can see that the argument will vary linearly with frequency. So therefore, this is called a linear phase function. Okay, this is basically the linear phase property. The phase varies linearly. What is the advantage of linear phase? Because the linear phase means that if you differentiate with respect to omega, then the group delay is a constant. Tau omega is equal to minus or is equal to plus nd. Okay, negative of the derivative, so the nd is a constant group delay for all frequencies. So this basically says a delay is an all-pass with respect to magnitude. It's a linear function with respect to phase and a constant with respect to group delay. Constant group delay. Okay, but the reason I wanted to introduce this was not for this, but to actually show you the difference between the principal value and the true phase. So let us look at that expression. Okay, so supposing I wanted to plot the true phase. The true phase starts at omega equal to 0 and goes in a linear fashion on both sides, with a slope equal to nd. Okay. Now, when it reaches, so basically this will be a function that will go on both sides. Okay. This is the linear part. So this is what we are drawing is the argument of He of j omega. Okay, this is omega. Okay, and just for our reference, it will cross minus pi and pi at the following points. It will cross it at pi over nd, and then this will be at minus pi over nd. It will cross 2 pi at 2 pi over nd and so on. Okay, so basically this will be 2 pi nd, and you can mark those points. Okay, now the principal value says once you reach minus pi, at this point what we do is we anything more negative, we add a factor of 2 pi. So what you will see is at this point, if you're plotting the principal value, it will jump up to plus pi, and then we'll start having the same function again. And when it reaches 2 pi, okay, when it reaches 2 pi, maybe I should try to see if I can get this a little more correctly. Okay, starts at pi, and then when it reaches 2 pi, no, when this is 2 pi. Sorry, so basically from minus pi I have jumped to 2 pi. At 2 pi I will this will be a function that will cross 0 here. Okay, basically it will go parallel, and the minute it touches minus pi again, it will jump. So let me draw it up to pi, and then after that dot dot dot, and here it will jump again. Okay. Jump to, so the difference between the true phase and the principal value. I hope you are able to see that and appreciate the difference. They're both saying the same thing in terms of the periodic function with period equal to 2 pi. Both will give you the same value in terms of the phase response, but important to note that the principal value, so this is the principal value. It always stays between the plus and minus pi. Now, you may ask the question, why not live with principal value? There is no problem, right? We can always. Most of the time, no problem, because if you're only interested in the phase. However, if I ask you to compute the group delay, then what will you do? You want to differentiate the argument, and the principal value has got discontinuities. A discontinuous function cannot be differentiated. So therefore, what you must do is, if you have to calculate the group delay, then what you need to do is to first compute the true phase. So we have the true phase, okay, versus the principal value. Principal value. This is needed for computing group delay. Okay, group delay will not work here because you will have discontinuities in your expression. So anytime we want to get the true phase, anytime we want to do group delay, we want to get the true phase. Sometimes we may want to also understand what is going on with respect to phase. If you see these discontinuities, sometimes it's a little bit difficult to visualize what is going on with respect to the phase response. So sometimes you may want to look at the true phase just to understand what is the behavior of the LTI system. Okay, but it's very straightforward. All you need to do is add or subtract a multiple of 2 pi, and then we can get the corresponding expression. So let me show you an example that's there in the book. And so this is the true phase. Okay, and draw lines, parallel lines, which will indicate the points at which you're crossing these multiples of pi. Okay, so look at the first point where you cross pi. It is still, the phase is still decreasing, but what happened? Because of the principal value, it jumped from there to plus pi, and then it stayed on there till it reaches minus 3 pi, because basically, because you've added 2 pi, and then once again there was a jump. Okay, so you can see the corresponding points and see where the jumps are occurring. Okay, and likewise, when you cross minus 3 pi in the other direction, again you will see a jump. So basically, this is the principal value. Principal value. Okay, now how are the principal value and the true phase related? You always have to add or subtract a multiple of 2 pi. So in the first region here, r is equal to 0. R of omega is 0. That means you don't have to add. Whatever is the original phase or the actual phase is the same as the principal value. Now in the second section, you subtract a minus 1 or minus 2 pi from every phase value that you see, then you will get the second part. And the third part in this region, you have to subtract minus 4 pi. Right, minus 2 times 2 pi, and so basically that is what will tell you what is the true phase, and therefore get us the value. So depending on where you are, and you can add or subtract multiples of 2 pi and get back the original response, and or get back the true phase. So I hope this example sort of gives you an idea of what the true phase and how the principal value will look different. But if you do what is called the unwrapping of the phase, so the relationship that we have is that the true phase, the argument of HE of j omega is equal to the principal value of HE of j omega plus some integer multiple of 2 pi. R of omega can be plus 1, plus 2, minus 2, basically some addition or subtraction of multiples of 2 pi. This process of computing the true phase from the principal phase is called phase unwrapping. Okay, what was wrapped around, you are doing the unwrapping, basically you're doing the reverse process. This is called phase unwrapping, and it's an important step that we must do in order to get the true or the unwrapped phase.